Hi, this is Professor Fernandez, and in this video, we're going to work out an example of using and working with Riemann sums. This example comes from the notes from lesson 17 in this Calc 2 course. You'll find those on my website, along with these other resources. So this example was meant to get you working with Riemann sums, specifically the left-hand Riemann sum, and also using some of the summation formulas. So I'll get there in a minute. One thing I'll mention is that there is a lot of setup involved here to work with Riemann sums and to think about what the concept means and to visualize it, with rectangles, areas of rectangles. So I really do encourage you to take a look at the notes for the lesson. They're again on that website I mentioned earlier. They contain all that setup, all the motivation, lots of figures, lots of intuition in there. So I'm mostly going to focus on solving the example in this video using a lot of those concepts. So the first thing I've zoomed in here to show you is the formula for the left-hand Riemann sum. Remember that the function we'll be considering here is y equals x squared. The left-hand Riemann sum takes the interval, whatever it is. In this example, it's going to be 0 to 4, and then it partitions it into a bunch of smaller subintervals. Usually it's an equal width subinterval. That's what we're using here with the left-hand Riemann sum. So all of these intervals have the same width, and that width is delta x. We'll talk about how to calculate that. And then we calculate the area of the rectangles with that width and with height being at the left endpoint of the interval, right? That's going to yield the left-hand Riemann sum. So we get this type of approximation, right? The area of all these rectangles, we add it up. That's the sum part of Riemann sum. And then we get an approximation to the area under the curve, which, right, would have been from 0 to 4 under x squared, this stuff. And we know how to calculate that using a definite interval. We'll talk about that at the end of the video. The point of Riemann sums is first to approximate that, to give you a numerical approximation. And one of the reasons it's useful is that sometimes we can't calculate the area under the curve using a definite integral. We may not know how to actually integrate the function. So you can always use an approximation like a Riemann sum. You may not always be able to calculate the exact area. So that's one of the main uses of Riemann sums. Okay, so I'm going to erase this over here. So this is the reason why the Riemann sum has this, the left hand at least, has this particular expression. Delta x is the width of these rectangles we're using to calculate the areas. F of this quantity, those are the y values of the rectangles. So the product here, this is the area of one rectangle, and then we're adding n of these rectangles, right? If you count from 0 to n minus 1, it's like counting from 1 to n, so that's n of them. So there are n rectangles here, and that's what explains the subscript over here. And then this thing in the middle here, this just keeps track of which x values you're using to plug into the function to get your y values. Again, because it's a left-hand Riemann sum, we're using the x values that are on the left hand endpoint of our subintervals. Okay, so again, I did my best to explain all of that fairly briefly in much less detail than I do in the lesson notes. So let's use some of that information to figure out what this left-hand Riemann sum is for y equals x squared on the interval 0 to 4, and we're going to use 10 rectangles. And then in the middle of the video, I'll show you a visualization of this using Desmos. I embedded a Desmos graph into the page on which you can find these lesson notes, and I'll show you how to use that, and I'll show you how to visualize this Riemann sum. Okay, so first thing we do in a Riemann sum is we calculate delta x. Again, this is a equal width partition, meaning that if we look at the interval from 0 to 4, the one we're interested in here, we are going to subdivide the interval 0 to 4 into 10 equal subdivisions. So delta x, the width of each one of those subdivisions, is going to be b minus a over n, right? This is b, this is a, this is n. So that's 4 over 10, that's 2/5. All right, so we're going to go 2/5. This is delta x equals 2/5, and that's the first endpoint, right endpoint of this first subinterval. And then we'll go another 2/5, another 2/5, another 2/5, and then end up at 4. After we do 10 of these, right? And we can verify that 10 times delta x is 10 times 2/5, which is 20 over 5, which is 4. Check. So there are 10 delta x's in here. all the way down to this last one. Okay, so delta x is 2/5. Next thing we do to calculate a left-hand Riemann sum is we calculate the x sub I. Again, these are the x values you're going to use to plug into the function to give you the y values for your rectangle heights. Okay, so a plus I delta x. This is again one of those formulas that pops out of doing this analysis and systematizing it. So what is a? A is always the left endpoint of our interval plus I times delta x. Delta x is 2/5. So this is 2I over 5. You might be wondering, what is I, right? So I, because it's a left endpoint, a left-hand approximation, Riemann sum, I ranges from 0 to n minus 1. So n in this case is 10. So I ranges from 0 to 9. So what does that mean? That means that, visually, if we look up here, we're looking at the left endpoint of these subintervals, right? So that's here, 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 and then all the way down to this one, right? We're not going to use x equals 4 and plug it into the function to get a rectangle height, because 4 is on the right-hand side of this last subinterval here, right? 4 is on the right-hand side. That would be something we do if we were doing a right-hand Riemann sum, but we're not. We're doing a left-hand Riemann sum. So all the x's, green x's you can see here, are the x values that we're going to use to substitute into the function in the next step to get our rectangle heights. You can see that if I look at any subinterval, right, the x value here of this subinterval from 0 to that is on the left-hand side. For this subinterval, the x value is on the left-hand side, so on and so forth. To the last one, the x value is on the left-hand side. So that's kind of the idea with the left-hand sum. Okay, so now let's do this last, well, not quite last, but this next step, I guess, of finding f of x sub I. So the function in this example is x squared. So I'm going to take this x sub I and I just square it. Okay. So I get 4I squared over 5. All right, so, sorry, 25. So I have my f of x sub I, and then what is the next step? Now I'm going to calculate the area of the ith rectangle. So that is number 4, step number 4. So that's f of x sub I times delta x, 4I squared over 25 times 2/5. So that is 8I squared over 125. So this is the area of the ith rectangle, right? If I go back to my graph and my picture, right, I'm looking at f of x equals x squared on the interval 0 to 4. And now, I've chopped up 0 to 4 into 10 equal width subintervals. If I were to pick any one of these subintervals, like this one right here, I know that I'm using the left-hand approximation, so I'm using that x value, and I go up to the function, I draw a rectangle. The area of this rectangle, a sub I, the area of the ith rectangle, is 8I squared over 125. So that's what I just calculated. Okay. And then now number 5, I'm going to add all of these areas as I ranges from, I erased it, used to be right over here somewhere, right? Remember, I ranges from 0 to n minus 1, in this case 9. Okay, so if I do this, 0 to 9, 8I squared over 125, that is L sub 10, right? I'm going to compare, right, this formula to this formula. So 10 is our n value. Here is the n value, great. Here's n minus 1, 10 minus 1, that's 9, great. And then we calculated all of this in the previous steps. Okay, so this is indeed the left-hand Riemann sum approximation. And now I get to use some properties of summation. So first of all, this is 8 over 125 times I squared. So one property of summation is that I can bring out this multiplicative factor in front of the sum. And then I'm looking now at the sum of I squared from I equals 0 to 9. So I'll zoom in a bit here. There are lots of summation formulas. I've written down 4 of the most common ones here. One thing to know about these 4 formulas is that they all start at I equals 1 and they end at n. Okay, so to apply them to what we're doing, we can't seemingly apply them because our sum starts at 0. But notice that the first term, when you plug in I equals 0, is 0 squared. So this sum from 0 to 9 is the same as the sum from 1 to 9. Because again, the first term in this sum is 0. And then every other term is contained in this sum. Okay, so now we can apply our summation formulas. So the sum of I squared, we look down over here, and goes from 1 to n. So n in our case is 9. So everywhere I see an n, like here, 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 I plug in 9. So I'm going to write down what the result is. So n times n plus 1 times 2n, that's 9 times 2, 18, plus 1 over 6. So I get 8 times 9 times 10 times 19 over 125 times 6, which, is what it is, right? If you calculate it out, it ends up being 18.24. So this is our left-hand Riemann sum approximation, right? So if I went back to my graph up here and I draw the left-hand sum approximation, and I just kept going here, okay, and then I added up the area of all of these rectangles, I would get L sub 10, which is 18.24. You can tell just by the picture I've drawn, however crude of a picture it is, that there is a lot of area that is not captured by the Riemann sum. It is an approximation, right? And there's all sorts of questions related to that. For example, how good of an approximation is it? That's a question related to the error. There's information about that in the lesson notes, and also we'll talk about that in the next lesson. But also, if we go back now to the function itself, right? This is a function y equals x squared. And if we're finding the area under the curve between 0 and 4, we know what that is, right? It's the integral from 0 to 4 of x squared dx. And we know how to calculate that. We find an antiderivative of x squared, one of which is x cubed over 3, and we use the evaluation theorem. We evaluate this from 0 to 4. So that's 4 cubed over 3 minus 0 cubed over 3. So 4 cubed over 3, that ends up being 21.3, repeating decimal. Okay, so you can tell that, it is an approximation. We got close. I wouldn't say we got super close, but again, we only used 10 rectangles. The idea with Riemann sums is that as you add more rectangles, you cram more rectangles in here, then, for example, if I took that one and split this in half, you're capturing more of the area. And certainly as n goes to infinity, if you take that limit and you get a number and a bunch of other conditions hold, then the number that you get is in fact the integral, right? The same as the area under the curve. Okay, so I promised you I would visualize all of this stuff. So I'm going to switch over to the website. So this is the site that I was mentioning earlier in the video that if you go to, you'll find the lesson notes. I'll just look on the left-hand side. Actually, let me bring up this pointer. So if you look over here on the left-hand side, this is the mobile version, right? So, but if you look on the left-hand side, you click on that, it will pop out. I'll do that in a minute. All sorts of information about the lessons. So what is this, right? So I've drawn here the function y equals x squared. There it is. I'll show you in a minute how you can change the function. This is the a and b value. I've set it for 0 to 4, and this is the n value, the number of rectangles. And then over here it says choice of method, set c equals 0 for the left-hand sum. I've set c equals 0. And this is the visualization that you get. So the interval from 0 to 4, we've chopped it up into 10 equal subintervals, and then we've drawn the rectangles whose heights are the left-hand y values, are the y values of the left endpoint of each subinterval. Okay, and then so the area, the green area, is the left-hand Riemann sum with n equals 10. Okay, so I promised that I would show you and scroll up here. So you can see in pane number 2 there, the function x squared. You could change the function if you wanted, right? Go in there, how about x squared plus 3? There you go, changes the function, or maybe x squared plus, I don't know, x. Right, so there's all sorts of things you can do here. So you can play around with this as you explore Riemann sums. We can also change the n value, right? So notice what happens as n equals goes greater than 10. We are cramming much more rectangles in there. There's much less white space between the rectangles, right? The horizontal green lines, and the function. So So as n gets bigger, we expect a better approximation. If you scroll down here I've actually put in pane number 10, there's the 18.24. This is the Riemann sum that we calculated. And then in pane 11, there's a 21.3 repeating. That's the value of the integral. Okay, so if I were to go all the way to n equals 20, then you can see we've gotten up to 19.76. So that's closer to 21.3. We've used 20 rectangles. So if I went to 200, 2,000, 2 million, we would get very close to the integral. Great. So last thing to show you is, again, I'm clicking on that left-hand side, and you can see that we are on lesson 17. So this is, again, where you would go to find the lesson notes. And if I scroll up this page, the lesson notes, there they are. And if you scroll down this page, there's information about practice problems. So these are linked to practice problems across the web that have solutions that you can use to sort of assess how much you've retained from this content. Great. Thanks for watching.